Hi folks, welcome to this video, and in this video I'm going to talk about the CAN bus, and I will discuss and explain some basics and some details. What I will not do is to repeat what you can read up in every wiki and textbook. I rather will focus on those points which, in my opinion at least, are most relevant for our hobby, that is RC models like drones, racers, copters, planes, ships, rovers, submarines, or whatever comes to your mind. Now, you might not be very familiar with CAN bus, and therefore I want to start with pointing out that this is not a new technology by any means. It's used for decades in the automotive world. So basically every car has CAN bus, and probably also your car uses CAN bus, and it's a very well established technology, and it's known for its robustness and reliability. I also want to emphasize that CAN bus is by no means a new technology in the drone world. So when you get yourself a DJI NASA, for example, which I don't know exactly, is maybe 10 years old or something like this, then this already uses CAN bus. Also, some open source projects like, for example, AutoQuad use CAN bus since many years. Also the Pixhawk flight controller, which I assume you're very familiar with, has a CAN bus ports on it, so the hardware is actually available since very long time. The CAN bus is also used in some do-it-yourself projects. For example, I've created the UAV CAN for hobbyist project, so you can read up the details on my webpage. And I started it about 3 years ago. So basically, since 3 years, I'm using CAN bus on my copter. The reason why the CAN bus might not be so much familiar to you is probably, I guess, to a large extent because it's relatively new to the autopilot world. So autopilot had been a bit slow in adopting this technology, but the good message is it's now coming, and it's coming strongly. And the second good message is that cheap but very good flight controllers which provide CAN bus to you are also becoming available. And an example is this Matek H743 flight controller, which is actually the motivation for this video, because in a previous video I was exploiting this flight controller and also its CAN bus capabilities. So what I want to do in this video is the following. I first want to briefly discuss the cases or situations where, in my opinion, the CAN bus is really useful, and the discussion will be brief in the sense that I will not present the arguments. So the arguments for my conclusions are, so to say, in the rest of the video. I will then discuss or compare the I2C, UART and CAN buses so that you better understand what makes them different. And in the course of that, we will touch things like open train versus push-pull and differential signals. And then there is a topic or a feature of the CAN bus which, in my opinion, is largely overlooked. And it's a feature I call the quasi optical isolation of the CAN bus. When there is this what I call the CAN 5-volt issue, which I will then discuss, and then I will come to the Matek H743 flight controller and discuss some aspects, and then of course I will finish with some conclusions and some final statements. So let me tell you why I think that CAN bus is useful for us, or what the situations are where it is useful in my opinion. And an important situation is that when you have I2C wires. I really think that you want to replace all of your I2C wires by CAN bus. And the reason is probably obvious. I mean, you know that I2C is very sensitive, it's not very reliable, it's prone to distortions, it's difficult to long run wires with it, and so on and so forth. So I2C wires is just a pain in the ass. So therefore, whenever you have I2C wires, try to replace them by CAN bus. I think that's a good idea. Another important situation is when you have ECs. So I think that CAN bus has quite some advantages when you use it with ECs. But I think also that this needs some explanation, and I will give you the explanation for my argument below. And the reason why this might be considered controversial is because CAN bus also has a disadvantage, namely that it's relatively slow. So when you use regular CAN bus, it runs at 1 megabit per second, and if you have 4 motors and maybe a protocol like UAV CAN, when one packet takes 110 microseconds. So when you compare that to all these modern protocols like the D-shot protocols, when you quickly see, okay, D-shot 150 is about 104 microseconds, so that's about what UAV CAN or CAN bus is. But D-shot 300 is already only at 50 microseconds, and of course this is getting better and better with higher D-shots. Now, CAN bus is of course then much better than PWM. However, it's also much worse than all these crazy D-shot protocols like D-shot 2400 or whatever else crazy is being used. So the implication is that UAV CAN is a big improvement in many cases, but it's not as fast as with modern D-shot protocols. That is, for racers, you don't want to use UAV CAN or CAN bus ECS. Another point or situation where CAN bus is really recommended is whenever you have long wires. And this directly points to application in planes. And it's really a mystery to me why CAN bus is not the #1 protocol, which is #1 bus system which is used in planes. And it's actually funny when you try to go back in time and research why Futaba has introduced the S-bus, when you find things like this here. So this obviously is a plane, right? And you immediately can see the reasons what they wanted to achieve. Namely, we wanted to have achieve a protocol or bus which allows for long wires, but which also can daisy chain, so that you only need few wires to get across all of your plane. And here there's actually a video out there of 10 years ago where this is very nicely demonstrated in this model case here. So this was obviously a main motivation for the S-bus, but you also know that S-bus is not based on CAN bus, it's based on inverted UART. However, CAN bus would give you the very same benefits as what is suggested here. So I would think that for planes, that's really what you want to have. There are, however, also situations where I think CAN bus is not very useful, it's more like a gimmick, and this is when you have UARTs. For example, for your GPSs. And UART is actually a very robust protocol. So you might not think that, but that's actually the case. And the S-bus example just showed you, or basically kind of proved this point. And I will later on explain why this is so. So with UARTs you really can run long wires, it's very reliable, and so there's not much reason, in my opinion, to replace it by CAN bus. I mean, if you get it kind of for free or you have it, it's a nice gimmick, it's a nice have to, but I would not see that replacing UARTs with a CAN bus gives a strong driving force or a strong argument for going to the CAN bus. So let me come to the discussion and also explanation of some basics, and also to the comparison of the three buses, I2C, UART and CAN bus. And here on this transparency I have collected some points which distinguishes these buses, and I will explain them now in the following. So what we have is the following. We have a I2C bus, we have a UART bus, and we have a CAN bus. And in all three cases the signal is transported by two signal lines. So in the case of the I2C we have a SCL line and the SDA line. In the case of the UART we have the RX and the TX line, and in the case of the CAN bus we have a CAN high and the CAN low lines. Now the single one feature by which we can distinguish these buses could be said to be, in the case of the I2C, open collector. And I should say that this equally well could be called open train. So it's basically the same. Collector refers to a bipolar transistor, while train refers to a field effect transistor. The characteristic feature of a UART could be said to be push-pull, and the CAN bus could be called to be differential. Now what does this mean? In the case of a I to C bus open collector means that we have an output which looks like this. So we have a transistor which on one side is connected to the ground, on the other side via a resistor is connected to VCC, which could be, for example, 3.3 volt. And the value of this resistor is typically for I to C in the range of 1 to 10 kilo ohm. And this is our output here. Now this resistor means that we have a high impedance output. And this has two negative implications. The first is that the signal lines very easily pick up distortion signals. So picks up distortions easily. And this is easy to understand. So if let's consider we have a wire which is losing free in the air. So it has a free end. Then this wire, of course, will work like an antenna. So whatever fields and distortions are around there, it will be picked up by this wire and produce some distortion signals. So this is the case of an infinite impedance. The opposite case would be to take the end of the wire and to short it to ground. In this case, there would be no distortion signals induced by whatever fields, distortion fields are around. So this is the case of a perfect low impedance. Now in the case of a I to C, we have a relatively high impedance, which means that the end of the wire is not very tightly shorted to the ground. It's pretty much a loose end, and therefore these wires can pick up distortions very easily. There's a second disadvantage which comes with this high impedance, namely that it takes a long time to charge and discharge capacitances. So we have a slow charge and discharge of capacitances. And the line of reasoning goes as follows. So when we have a high impedance, this means that we also have only relatively small currents which we can drive through the wire. Now if we want to change the voltage of the wire, then we need to know that a wire is also a capacitor. So we need to charge or discharge the capacitor which comes with this wire, and this is being done by a current. So when we have a low current, then we can charge and discharge this capacitance also very slowly. So you see the high impedance implies a low current and therefore a slow charging or discharging of the capacitances of your wire. And indeed, when you look at the signals with an oscilloscope or something like this, then they typically look like this. So this could be 0 volt. Then there would be a threshold by which you could detect a high, and here there would be 3.3 volts somewhere here, and this could be a logical 0, this could be a logical 1, a logical 0, a logical 1, and so on. And you see that because of a slow charging of a capacitance, we get this curve here, and we only have a relatively small overhead to detect our logical 1. So if there are some distortions in here, when we have only a small voltage range which can be accepted by this. A second consequence is that if you use, for example, a longer wire, then the capacitance of the wire becomes larger, or you just wire your wires badly so that they have a large capacitance. And when you have a larger capacitance, then the signal might look like this. So it's even charges slower than before, and in this case you see that you don't even reach the threshold limit to detect the logical 1, and the bus will not work at all anymore. So you see these two consequences have a bad impact when you use long wires, and also makes your bus relatively slow. Now, how does it look like for the UART? Here we have a push-pull configuration. That is, we have an output which looks like this. We have two transistors which are connected roughly like this. And this is our output here. And here now we actively push the output signal to either the ground or to the VVC line. So we basically achieve very low impedances towards both directions, and therefore the signals usually look very nicely and very sharply like this. So this could be 3.3 volt, this could be 0 volt, and this would be a logical 0, a logical 1, and a logical 0. So here we achieve really low impedance in all situations, and therefore we overcome all the problems with the I to C bus. So we have a very rough, so the wires are very robust versus distortions, and you also get a very charging and very fast charging and discharging, and therefore this makes it good for long wires and also relatively fast. And I want to mention that the same principle applies to the SPI bus, for which you know that this is very often used for high data rates. Now, how is the situation in the case of a CAN bus? And here we have two signal wires. We have a CAN high and a CAN low. And in normal conditions, both are at 2.5 volt. And this would correspond to a logical 0. Now, if you want to write a logical 1, what is happening is that you raise the CAN high voltage to a level of 3.5 volt, and you lower the CAN low level to a voltage of 1.5 volt. This would correspond to a logical 1. And the signal which you're reading when at the end is simply given by the difference of these two signals. So the signal is CAN high minus CAN low, and this minus sign is what makes it differential. And now we can test the consequences of that. So that we have a logical 0, what we do is 2.5 volt minus 2.5 volt gives us 0 volt. So we measure 0 volt and then identify this as a logical 0. And in the case of the logical 1, we have 3.5 volt minus 1.5 volt gives us a 2 volt, which you would identify as a logical 1. Now, the advantage which you get by this principle, in addition to the advantages of this push-pull configuration as for the UART, is that distortions are also cancelled out. And also this is easy to understand. Let's assume that we have a distortion which affects both signal wires the same way, maybe induces an additional voltage of 1 volt to each of the wires. So then we can repeat the math. So for the logical 1, we measure now a voltage of 4.5 volt minus 2.5 volt, and we get out again 2 volt. So that when we have such a equal distortion on each line, which is then called a common mode signal, then this is perfectly cancelled out. Further advantage of this differential pair is that also the capacitances, stray capacitances, become smaller, so they are reduced. And as we have learned from the discussion on the I to C bus, this makes it that you can charge faster and slower, so that the bus becomes also faster. So, and altogether, this is the reason why you get a robust and fast bus here. So what I want to mention is that this differential idea is not unique to the CAN bus. It's in fact used in many buses. For example, it's used in USB, where you have the D plus and the D minus lines, which form such a differential pair. You have the HDMI signals, where you also have this differential pairs. You find this also in the Ethernet principle, where it's used, and it's used in many more other for exactly these benefits. For these reasons, it's used in many other buses too. I also want to add in that these two features, the minimizing the distortions and the capacitances, can be largely helped by using drilled wires. So by using wires which go like this. So this minimizes distortions or helps canceling out the distortions and also reduces the capacitances. So what this means is that you always should drill your CAN high and CAN low wires nicely together. And when you get really a very, very good transmission system. There's a last point I want to mention, which is about the I2C. There is actually efforts going on to improve I2C. And I want to show you this because it really nicely fits into the story here. It's then called ICCC. So this is a relatively new suggestion. Here you can see something like 2017, here 2016. So that's relatively new, and that's why it's not yet really available to us. But the point of interest here is the following. So there is a comment down here what this ICCC is doing. And it's the sentence here. So the primary difference is that I2C operates them as open train outputs at all time. So its speed is limited by the resultant slow signal rise time. And this is exactly what you understand now what this means. This is what we have discussed for the I2C bus. While ICCC uses open train mode only when necessary for compatibility, but switches to push-pull outputs whenever possible. So it exactly does it what we have learned now is a good thing to do, namely to have this push-pull output configuration. And this brings us directly to the next feature of the CAN bus, namely the feature which I call quasi-optical isolation, and which, as I mentioned in the introduction, is a feature of CAN bus which I think is largely overlooked. So what we want to talk about is quasi-optical isolation. Now, what is optical isolation? So here you have two signal wires, and when you do something, usually it's a diode and so on, and you transfer the signal to another output. And what this is doing, so that when you have here a signal, when you get exactly the same signal out of that, and there's this optical isolation, which means it's a non-electrical isolation, and therefore this system works without problems, even in the presence of large potential differences. There's no direct connection between the ground wires or something like this. So the voltage on the output will be the same as the voltage on the input, independent on such potential differences. And now I'm arguing that a very similar behavior is also provided by the CAN bus, by this differential signaling of the CAN bus. And I want to discuss this by means of an example. So let's consider an ESC, which we want to power. So we power it here from 0 volts and here from some battery. And we want to make this example a bit more realistic and accept that in the wires there is some resistance. So it actually looks like this. And let's assume, for the sake of example, that this is 0.1 ohm. And let's also assume that we want to drive 20 amps. Now, what this means is that at this point we indeed have 0 volts, as we are thinking it, we are expecting it, but at this point here we have a voltage of 2 volts. Now, what is the consequence of that? Let's assume that we also have a signal wire in order to control our EC. So this could be a PWM signal or a D-shot signal or whatever, and we want to write a 1 here. And let's also assume that in order to have a 1, we need to have a voltage of 2.5 volt. However, what you can see now is that the EEC is not seeing this 2.5 volt. The EEC is seeing only 0.5 volt. And it probably will read the 0.5 volt as a 0. So basically what you're seeing, that under this condition, the controlling of the EEC will not work properly anymore because of this potential shifts due to this currents and resistances of the wires. And this is not an academic example. There's actually one example out there, at least one example, where this miserably failed or produced miserable results, and this is the 3DR Solo, which came out 5 or 6, I don't know, remember, years ago. And in this 3DR solo, the EC power supply and so on was really badly designed, and it suffered heavily from exactly this phenomena which I was describing. And you can, I mean, it was a big story, big mess, so you can research this in the internet and you will find many discussions around it. And there had been all sorts of solutions. There had been software solutions to which kind of reduced the current which this motors were allowed to take, which obviously reduced the capabilities of this drone quite a bit. There have been hardware solutions to replace the flight controller and other solutions and so forth. And one solution I was doing a few years ago for my 3DR solo is that I was using the CAN bus in order to overcome this problem. And you may already guess why this is working, but I nevertheless want to present this in detail. So we have the same situation here. We have here our AC. We power it from our battery. We have also resistances in our wire, or ohms, sorry, 0 volt. We have here our battery. Okay, and again we drive 20 amps, so we again have a situation that here we indeed have 0 volt, while here we have 2 volts, but now we have CAN wire. So we have here CAN high and CAN low. And again we assume that we want to write a 1, that is, here we have the voltages of 3.5 volt and 1.5 volt. However, the signals which the EC is seeing is now the following. So we also have this 2 CAN high and CAN low signals, but the voltages on CAN high is now 5.5 volt and the voltage on CAN low is now 3.5 volt because of this additional. Sorry, this is wrong. It's the other way around, of course. Sorry. So the voltages here is just 1.5 volt and the voltage here is minus 0.5 volt. However, as explained, only the difference between these two signals counts, and we can test it now. 1.5 volt minus 0.5 volt gives again 2 volt, which we realize is a logical 1. So basically what this differential signaling is also doing for us is to compensate for this common mode voltages, for this potential shift in such situations. And this is my argument why I'm saying that the CAN bus can be very useful for ECs, especially when you have larger drones where there can be larger currents, longer distances, and so on and so forth. This property of a CAN bus should be a very useful property. Of course, the CAN bus is not an optical isolator, so it just works within some range like that. And in order to exploit what this range is, we can look at the properties of typical CAN bus devices. And here, for example, in the Matek H743 Wing, there's a so-called CAN transceiver used, which I will discuss in the next section, and which is of this type. And so we can look up, so on the CAN high and CAN low signals, you can apply up to 58 volts. So that's really a huge overvoltage, right? I mean, we are working with 1.5, 2.5, 3.5 volt, but it can be as large as that. And the differences between CAN high and CAN low can be maximum 27 volt. So what this means is that this common mode voltage, which caused the problem here, does not only have to be 2 volt. The CAN buses can handle, I mean, the standard says 7 volt, but modern CAN buses can handle 20 volt, 27 volt. So within this voltage range of this 20 volt, plus minus 20 volt, the CAN bus works like an optical isolator. And I believe that for many applications, this can be very useful when in terms of EC. So let's move on and discuss the CAN 5 volt issue, as I call it. And the key point to realize here is that you cannot connect the CAN high and CAN low lines directly to your MCU. So this is different to the I2C or UART or SPI buses, which are directly supported by the MCU. In the case of a CAN bus, you need to put in between a CAN transceiver, which translates between the CAN high and CAN low signals and microcontroller compatible lines. Now this is an electronic device, and therefore it also needs to be supplied with some power. So you have a situation that the MCU is supplied typically with your 3.3 volts, but also the CAN transceiver needs to be supplied now with some voltage. And the CAN transceivers can be broadly classified into two categories: the ones which can operate the 3.3 volt, so you have VCC equal to 3.3 volt, and the good thing about them is you can see this directly, that you can directly power it from the same supply which you're using for your microcontroller. So I say this is compatible with the MCU, with your microcontroller. The downside, however, is the following. If you recall it, the CAN high signals go from 2.5 volt to 3.5 volt. And 3.5 volt is obviously larger than 3.3 volt. So what this means is that such a CAN transceiver cannot produce the correct CAN high signals. So what these devices generally are doing is that they are cutting this CAN high signal short to some much lower levels. Let's say even just 3 volt or 2.8 volt. So but you lose a significant benefit here by cutting this down. So therefore the downside here is that these transceivers are not compatible with CAN. So what this means is they perfectly work fine under normal conditions, but they give you this disadvantage that this CAN high is not as good anymore as it was before. Okay, but otherwise that's a very safe and reliable solution. You just connect your CAN transceiver to your 3.3 volts and things will work reasonably well. Now there's this other type of CAN transceivers which work with a voltage of 5 volt. Now you immediately see that this problem of this CAN high signal is no problem anymore, because with a 5 volt electronics you easily can produce a 3.5 volt signal. So therefore the good thing is here that these are fully compatible with CAN, that is, you get the full advantage of your CAN. So you get much nicer signals, much larger headroom for distortions, much more robust CAN bus. The downside, however, is the following, that you somewhere need to get this 5 volt from. Okay, and there are two sources in your system usually. So one source for this 5 volt is that you have a USB plug, or you have an external battery eliminator, BEC, which produces your 5 volts. And these are usually connected in such an OR scheme so that you can use your electronics from either way. So you produce a high voltage, and then from here you derive via an LDO, you derive your 3.3 volt. Okay, so that's a typical scheme which you can use. But when you immediately see what the problem here is, so these diodes usually have a voltage drop of 0.3, 0.4, 0.5 volt, depending on which you're using, depending on what current is flowing. So let's write down here 0.54 volt voltage drop here, and this is of course also on the USB. And now a USB power is usually not even 5 volt. So it's usually lower, in particular when you also draw some current, so it might be just 4.8 volt or something like this. So what this tells you, that when you have such a power scheme, that the voltage which you supply to your CAN transceiver is not 5 volt. It can be substantially lower than that, in particular when you're using a USB port. And many CAN transceivers, many of these 5 volt CAN transceivers cannot handle this situation. So they will basically shut off. What this means is that when you supply your system from a USB power, your CAN bus will not work or might not work. So this is a downside, that this is not compatible with USB. So you can get issues from that. Now, there's an additional thing you might think, no, okay, so we have here on our current plug, we have here this current 5-volt line, so why not just connect it like so? So we power our current transceiver from this current 5-volt line, and it gets 5 volt, and then this everything is all right. And this is true, and for many situations this will work without any issues. However, it's a point of failure. So things can happen like that you have a short overvoltage, and what this means then is that in such a scheme the current transceiver might be just killed. And I'm saying this not just as a theoretical considerations. I actually had a user of my UAV CAN nodes who had exactly such a situation, and then all of his current electronics, including the flight controller, got destroyed. Because what has happened, the overvoltage on this current 5-volt line destroyed the current transceivers, which in turn burned through and then destroyed more electronics on these nodes. So this is really a point of failure. And that's what I want to emphasize here. What you want to do actually is, well, if you want to power your current transceiver from the current 5-volt line, or then what you want to do is that you want to have some protection in here. And protections, and a proper protection, in my opinion, should include, of course, an overcurrent protection like a fuse, but also an overvoltage protection, and ideally even a reverse voltage protection. So then you would have really a reliable, robust current bus system. But the issue here is that many of the so-called, also of the high quality, so-called high quality products from high quality manufacturers don't actually do that. So they very often provide you either no protection at all, or just a very rudimentary and basic and not fully safe protection mechanism. So this is really a big downside, that usually you would want to have a safe and protection of your 5-volt supply chain. Okay, this is actually a very complicated topic, and with many aspects and this and that. So you'll find a page on my web page where I'm discussing this at some length, but I don't want to go into more detail here, and just besides mentioning this to you, that this is a problem. So what I'm doing in my designs is that here for this diode, for the USB, I'm using a so-called ideal diode, so that the voltage drop here is essentially 0 volts, and this is usually sufficient to ensure that also your current transceiver is working even when you supply it from USB. And the second thing I'm doing is that here I have some overvoltage and some overcurrent protection, as well as some reverse voltage protection, to avoid that really your electronics is getting killed from that. Okay, so this is what I wanted to tell you about this issue. You cannot do a lot currently about that, because the hardware manufacturers have not really come up, at least as much as I know them. I mean, I don't know any hardware products out there, of course, but as much as I see it, this is largely not well resolved so far, and for many cases it won't be a problem, except of the nuisance that your CAN bus might not work when you power from USB bus, but it's an intrinsically non-reliable situation here, compromising the robustness of your CAN bus. And with that, I'd like to come to the last topic which I want to cover in this video, namely discussing the Matek H743 Wing flight controller. And in this flight controller, we are using a TGA 1051 CAN transceiver, and I should say that this is actually an excellent CAN transceiver. So it's produced from NXP. And NXP, I'm not sure if they are really the number one, but they might be the number one in the current business. So very well renowned manufacturer, and all these current devices are used in the cars and so on and so forth. And this is a current transceiver of a so-called third generation, and it's really top notch. So it has all the bells and whistles which you want, which you expect in a modern current transceiver. And it's a 5-volt current transceiver. And when it's really a good one, you can see here that from these impressive numbers you have seen before when you talk about the current high and current low voltages and so on. So I mean, this is really super robust and reliable. Okay. The reason why I'm a bit concerned about this current transceivers are the other numbers. And I should say that I myself am using these current transceivers since the 3 years I'm using current nodes, and I never had an issue with them. However, I mean, I also never had an issue with PWM or with UART lines and so on and so forth. I mean, this would be the argument that because one doesn't have issues very often with that, and one doesn't have to go to CAN bus at all. I mean, we are talking about also reliability and robustness, right? And these numbers make me a bit worried. And the reason, for example, and when you look at this under voltage detection, it's given as 3.5 to 4.5 volt. And I mean, if it would be always at 3.5 volt, I would be totally happy. But if it's, let's say, you get a device which is at 4.5 volt. So one implication of that would be that, I mean, it would be very difficult to operate this from USB for setup and so on and so forth. So USB might easily fall below 4.5 volt, and then the current bus would shut off even if you do the power scheme accordingly. But there's another point which concerns me most. I mean, let's consider that in flight, for some reasons, I mean, it should not happen, but it can happen, that the voltage momentarily drops, let's say, to 4 volt. Okay, so it might be for a few seconds, it might be for a millisecond, I don't know, but nevertheless it might just drop to 4 volt. And the sad thing is that all of your electronics would still continue to work at this 4 volt because it's 3.3 volt electronics. So I mean, the flight controller would still work, the ECs would still work, the magnetometer would still work, the GPS would still work. So I mean, all this electronics would still work, but nevertheless your copter would fall out of the sky because not because the electronics fails, but because you shut off the current bus, your main communication backbone. And I mean, this doesn't feel right. You know, I mean, everything is still okay and would run fine, but you nevertheless will crash just because of such a thing. And so therefore I'm not totally happy with that. So as I said, I'm using this myself since long, and other flight controllers use it. So and it's a top-notch transceiver, and one can't really complain towards Matek that they are using it. I mean, it's a good choice, and it's recommended by the drone code standard and so on and so forth. Nevertheless, after this 3 years of experience with CAN buses, I would not use it myself anymore. So if I would redesign my CAN nodes, I would not use this transceiver anymore. So this is a figure of concern. And you also see the supply voltage. I mean, it doesn't have lots of room for over voltage and so on. So I guess I would rather choose a different current transceiver nowadays. And there's a second point I want to mention, and it's about the power scheme in this Matek flight controller. And it's shown here. So it's this current transceiver, and here you have your battery power supply. It's going through a switching regulator which produces 5.0 volt, and then there's a diode from which one takes off this, what they call this 4.5 volt line, and in parallel to that you have another diode which goes to the USB bus. But now you can see that the current transceiver is directly connected to the 5 volt line and not to the 4.5 volt line, so that when you power the system from USB bus, there is no voltage going to this 5 volt line, and therefore no voltage going to the current transceiver. That is, when you operate the system from USB, the current bus will not work. So this is not a technical issue, but it's annoying for setting up the system and so on and so forth. Okay. So what I said, it's not a technical issue. So in flight, it will be pretty fine because here you get directly from the 5 volt line. And in some way, the decisions which we have made here is not totally bad, right? I mean, if you have to make it simple, which means that it's also cheap and that's also small in size, it's not a bad decision to drive the current bus from this 5-volt line and not from this line here, and then to connect the current bus to this 5-volt line, and also to connect the telemetry unit to this strong 5-volt line and not to this 4.5-volt line. So they obviously have thought about what they're doing here, and it for many situations will be just perfectly fine, so I'm not complaining here. So it's not a totally bad decision, but nevertheless we have the issue that there is no protection at all in here. So I definitely would hope that in some future flight controllers the manufacturers would pay a bit more attention to this protection of this 5-volt line here, of this current transceiver, and this under and over voltage protection. And we also have an issue that we can't operate the system from the USB bus. Okay, so this was a long video again, but now it's time to come to the conclusions. And I just put up this transparency here again. So I hope that in this long video you found the information you wanted to know in order to judge whether you want to use the current bus or not, or in which situations it might be useful for you. I hope that you also got a bit of a technical background and of the electronics behind it to put your judgment on a firm and proper basis. And besides that, I think I don't have anything to say anymore. So thanks a lot, guys. See you next time.